All right, so the linearized model. So one nice thing, as we'll see, that this flow model by Brown-Wood back in 1989 has a very nice linearized model. This model is much more suitable for distribution systems compared with, let's say, DC power flow model, the linearized model that we saw yesterday. So for example, you does not assume the lines are lossless. So the RJK for on line JK can be large. It does not ignore reactive power. So reactive powers are in the model. And therefore you can consider, for example, Vauban control that we mentioned yesterday or earlier today as well, where you want to control the reactive power output of a inverter, for example, in order to help stabilize the voltage on distribution systems. It also doesn't assume, say, the voltage angles are small because there's no voltage angle. Not only is the linearized model more suitable for distribution systems. Oh, it says my internet connection is unstable. So is internet fine?
We lost you for a few seconds, but I think it's better now. You can try again to continue.
Okay. Otherwise, do let me know and I can switch to a Wi-Fi device. Thanks. Okay. So what I said is that the linearized model has many advantages for distribution systems, not only because this flow model, whether it's linear or nonlinear, is much more suitable for distribution systems for the reasons that I mentioned. Hopefully, you do get, yeah. But also the linearized model in this flow the linearized this flow model also has very nice analytical properties, as we'll see in a moment. And the two important features of this analytical property. One is that there's explicit solution. Given the injections, you can compute the voltage and the branch power flows explicitly in closed form. And that makes it very convenient for example, in some analysis, but also in computation. We make use of that for to approximately compute, say, the gradient projection algorithm for large networks. And the approximation is quite reasonable, but because it's linearized model, the gradient becomes constant. So that's extremely convenient. The second thing with the linearized model is that the solution of the linearized model actually provides a bound or the solution of nonlinear model. And therefore, there's a very clear relationship between the linearized model or its solution with the nonlinear model, which is more accurate. Right? Now, it's not very clear for DC power flow. What is the solution? A solution of a DC power flow equations relate to the solution of the AC power flow solution. We know it's an approximation, but it's not very clear whether one bounds the other and so on. It probably doesn't, depending on the situations and so on. But there is a clearer connection between the linearized model and the nonlinear model in the disk flow model. Okay, so let's look at that. So let's start with the disk flow model. Again, the equations are the J to K as JK equals so this is the outgoing power, sending end power from node J. And this is, let me use the orientation where all lines points away from the from bus 0. So this will be Sij. I is the unique parent of node J minus Zij Lij plus Sj. So that's the power balance. Then there's a Vj minus Vk 2 times let me write this out explicitly. So this will be 2 R JK PJK X JK QJK minus RJK square SJK XJK square and then LJK. And then there's a VJ. So this is the original disk flow model. In the linearized version, all we do is set LJK to 0. So this disappears, and we don't have this. That's the linear model, right? So the linear model becomes just this without this. Right? So we can move it closer. Okay, so this in this model, the variables are the real and reactive power injection, so small p and small q, the branch power, and the voltage magnitude square. So these are variables. So given Sj for j not equals the substation. So think of that as loads, but now they can also be generations because of distributed generation. But given all the injections except for from the customers, except at the substation, and given the voltage at the substation, the power flow problem is to determine the remaining variables, which will be S0 at the substation, capital SJK for all lines, so capital PJK and capital QJK for all lines JK, and also VJ for J not equal to substation. So that's the power flow problem. Well, it turns out you can write down the solution explicitly in closed form, and the solution actually has very nice properties. Okay, so let's do that. So the easiest way, so we can just iterate on this and figure out what the solutions for the line flows and then the voltages. And once we get the line flows, we can get the substation injection just from these two equations above. But the easiest way to see all this and also to talk about some of the analytical properties of this power flow solutions for the linearized model is actually write this in vector form. So if once we write this in vector form, things becomes very clear what the structure is and what the solutions, explicit solutions are. Okay, so let's do that. So to write this same model in vector form, we need the instance matrix that we mentioned yesterday. So let's do that. So the instance matrix is m plus 1, the number of nodes, times m, the number of lines. But because it's a single phase and tree, this is n, capital N, number of lines. And so we call this C bar with a bar that will include the substation bus 0. Later on, we'll look at a submatrix of C bar, which removes one column. One row, sorry. Okay, so C bar of node J line L equals 1 if the line is of the form from J to some other node K. So it's an outgoing. So if J is the outgoing node for line L, it's -1 if it is incoming. So it's I to J and then 0 otherwise. Okay, so that's it. Then in terms of the instance matrix, this this is simply the power balance, is simply the injections. So this will be Sj for J0 to N. Okay, so this is this vector with a bar. That means it includes the substation bus. Okay, equals C bar of S. S is the branch power flow. Okay, and the second equation here in vector form will be C bar transpose V, which is the vector of voltage magnitude squared, equals 2 times the diagonal entry of the resistances on the diagonal, the capital P, which is the line power, the real line power vector, and then the diagonal matrix of the reactances and the Q. Okay, so this is a diagonal of R JK for all the lines JK, and this is diagonal for X JK for all line JK, right? So you just get simple diagonal matrices on the right-hand side, and then the instance matrix on the left-hand side. Okay, so this is the linearized this flow model. Now we understand a lot about the instance matrix. So it's n+1 by n. It has rank n, so it's not invertible, but the null space is a span of 1, and it has all this lots of interesting properties that's understood. Moreover, we can solve these set of equations explicitly very easily. So the way to do that is look at so C is this slightly tall matrix. So this is n+1 rows, and these are n. And we separate this into C, small c0 transpose. So this is the first row of the C bar matrix, and then the remaining, just call them C. So C is n by n. And C, one can prove, is always invertible. If you remove any row from the C bar matrix, you get an n by n invertible matrix. So this is called reduced instance matrix that is invertible. And in fact, its inverse is very simple and has very nice interpretation. Okay, but let me. Okay, let me let me. I can't help but this inverse has this very simple interpretation. So details in the notes. So so this is Lj, right? So the inverse is L for line L J node is -110. If line L is in the path from the bus 0, which is the root of the tree, to node J. If it is in that path, but in the other direction, then it's 1 else. Okay, but in any case, so, it's not important as long as we know that it's invertible, and it doesn't matter for our purpose that it has this nice simple structure. So you can solve this, right? You can solve this set of equations using the inverse. So the first row of the power balance equation is simply S0 C0 transpose, which is a given vector that is the first row of the instance matrix. times S. So if once we have solved for the capital S, which are the branch flows, we can compute the substation power easily. So that's this. And then the remaining ones are S without the bar, that is the remaining power injections that are given. So this is a given quantity. Oh, okay, so let me write the other direction. So the branch power is the inverse of the injections, okay? And then the V from the second equation is simply V0 of 1. So V0 is the substation voltage magnitude squared. 1 is a scalar. 1 is the vector of all ones. That's the one vector. Plus, plus 2 times some matrix R times the injection, real power injection at the other nodes except the root, some matrix X times the reactive power injection, right? And therefore, given the power injections, small s, at all nodes except the root, we can write down explicitly the solution for all the other variables. Okay? Now, moreover, the matrix R and X is very nice. It's positive definite. Is C inverse D of R C inverse of C inverse transpose. Right? So C matrix is n by n and invertible. That's this, and this is simply transpose. And DR is the diagonal matrix of resistances. So the whole thing is positive definite and invertible. Similarly, X is also invertible. So this is C dx C minus. And therefore, you get this simple explicit solution for linearized model. Now, you can also write this out explicitly for each components and everything. It's a very nice interpretation of what's going on. Okay, so let me go to just state some of the nice properties that we'll use for the mobile control application. Okay, so one is that solution, the explicit solution that we saw, right? Given the power injections. Secondly, you can write down, you can solve that explicitly, and you get Sij. Let me denote this by the linearized model. That is, if you solve this quantity on line ij, so this is linearized. So let me maybe add, this is linearized. V is also linearized. Right. So the solution of this set of linearized disk flow. Then this is Sk minus K in the tree of J. Okay, so this is I, this is J, and we ask what is Sij, the linear for the linearized model, right? From the sending end from I to J. Then you look at the tree rooted at node J, including J, and look at the injections, right? So every bus here, there's an injection. You sum up all the injections in the subtree rooted at J minus the Z is this, right? And therefore, all this says is that the line power coming to J equals all the negative of the injection. So think of negative SK is the load, right? Then all the low power in the subtree rooted at J is supplied by this Sij lin. That's what it says, right? So it has a very intuitive physical interpretation. Third is that the voltage, you can also has a nice relationship with, so it's VC, you can propagate all the way back to the root, is 2 times say RJM PM XJM. So this is simply just write out the explicit solution here, but it has a nice interpretation, physical interpretation. Now, what is this? This is the following. Well, let me write this down first. IK in the path of PJ and PM. Okay, so you look at our so J and M. So you look at okay. So first of all, what does this mean? It means that the voltage at node J depends on the injections at other nodes, the real power injection and the reactive power injection PM and QM at other nodes M. What is the dependence? Well, you look at the following. You look at the node J where you want to compute Vj, and you look at a M, node M, where it depends on the PM and QM. Okay, so this is a substation bus zero. There's a unique path from 0 to J. There's a unique path from 0 to M. The resistances, the sum of the resistances on the common path, that's RJM. So that's this. You sum the line resistances on the lines that's at the intersection of the path from 0 to J and from 0 to M. That's what RJM is. Similarly for XJM. So you sum up the reactances. So that's what it is. It depends on the impedances on the common path. Now, moreover, you can show the relationship between linear and nonlinear solutions. Okay, so you compare Sij and Sij lin. So Sij is the power flow solution from your original nonlinear disk flow model, which you can think of as the reality. It's more a realistic model. And then you think of the Sij lin as an approximation of this, right? It's a solution of the linearized model. Then there's a very clear relationship, which is that the linearized power flow underestimates the nonlinear solution power flow. Okay? And the voltage of the nonlinear model is upper bounded by the voltage in the linear model. So the voltage square magnitude overestimates the voltage in the nonlinear model. Okay, so so these are the important properties of linearized model. Let me check the time, 10:20. I have 10 minutes. Okay, let me discuss an application of this linearized model briefly. So this is the overall control. Okay. So what we're going to use is the explicit solution V equals V01 plus 2R times P minus P hat plus XQ minus Q hat. So let me explain what this is. So P is the vector of real low power or power injection that's not controllable. It can be positive or negative, doesn't matter. So yeah, but it's a real injection that is not controllable. P could be the controllable real power for some applications. So I want to separate those injections that are not controllable from the injections at the same bus that is controllable. But for vulvar control, we're going to assume neither is controllable. So for example, this P hat may represent the real power load. This P can represent the solar generation. So this is something that we measure, but it's not quite controllable. Okay, I guess you can control by curtailing, but for the example that we're going to go through, we are going to assume P are not controllable. And similarly for the Q. So Q bar is uncontrollable injection, reactive power injection. You can think of that as a low. And then the only controllable variables are the Qs. So this can be the output of the smart inverters. Right? And therefore, we can write this as V, which is a function of the control Q, to be 2x times Q plus everything else. So everything else will involve V0, the RP minus P hat. So let's just call this V tilde. So V tilde is given. And therefore, this is how the system will behave, right? At least in an approximate linearized model, that given the control Q, the V that will result is given by this very simple linear relation affine function. Right? So the control, we're going to assume must live in the following box. So QJ, the control, has to be chosen within the control set, right? Admissible control, which is the set of Qs that has a certain bound, upper and lower bound. Right? So in the smart inverter case, for example, then so this is PJ, QJ, given a solar generation, PJ that is fixed, then QJ may be restricted to this line. It could be some point in this space, if you can also adjust P, for example. So that just depends on the design of the power electronics, what can be changed, what can be controllable, and so on. So for now, we're going to assume we restrict the control QJ to be in some bar, in some box, right? So there's an upper bound, lower bound, which could be determined by the P, but they are given. The upper bound, lower bounds are given. Now, notice the important thing is that we're going to require the control that we choose is local, meaning that we're going to restrict ourselves to control of this type. So think of this as iterative, right? Then the control is going to be of the form, the local control, that it is a function, control function UJ. Okay. So UJ is the thing that we're going to design. That's the control law. But UJ can, excuse me, can depend only on the local voltage. That's the key. So it depends on VJ only, but not other voltages on the grid. And VJ depends on the previous control Q vector. So it depends on all the Qs on the grid at time t, minus the reference. So there is a nominal voltage. So VJ of reference, the reference can be different for different node, right? So again, the control structure is such that given the current voltage, which is determined by the control, the entire vector of controls in the previous iteration QT. Given this voltage, you look at the error from, so the deviation from the nominal, from the reference, ref, which is given. This is the error term, and your control UJ can depend only on the local error. And there's a, say QJ, so, and then you saturate at lower and upper bound of your reactive power, okay? Okay, so that's the control. How does it behave, right? So this is a local control. Each smart inverter, QJ, will measure its local voltage, look at the error, a deviation from the nominal, and then choose a control action QJ t+1, and then the whole iteration will repeat, and we ask, will this converge? And can we characterize if it converges, can we characterize the equilibrium point? So using this simple model, one can prove that indeed it will converge under certain conditions, and the equilibrium point has a very nice simple interpretation. Okay? It's a solution of a certain optimization problem. Okay? So let's state them precisely under two assumptions. One is that the control function are differentiable, and also the gradient is bounded. Okay, so there exists alpha j such that the derivative uj vj. So u is a function only of v, right? So given a certain voltage, in this case is the error, but given certain voltage, you have a uj, and you look at its derivative, its absolute value is bounded by alpha j. Okay. The second assumption is that the uj are strictly decreasing, which is a common control policy in practice, where if you have a higher voltage, then you decrease your reactive power. Okay, so then you can show using this linearized model that this is convergence. Okay, suppose C1 holds. Then the stability condition that is required is sufficient but not necessary, is that if the singular value, the maximum single value of AX, where A is the diagonal matrix of the alphas, is less than half, then there is a unique Q star in the admissible control set. Q star is the vector, the control vector that is admissible within the box, the range, and QT converges to this unique Q star geometrically, exponentially fast. That is, if you look at the distance of qt vector, this is less than some beta to the power t of the initial distance for some beta between 0, 1. Okay, so under the stability condition, which we can compute, X is the diagonal, X is this matrix. This is positive definite matrix here. Weighted by a diagonal matrix of the upper bounds of this, right? So diagonal matrix of alphas. So you multiply, you look at this matrix, you compute singular value, look at the larger singular value. If this is less than half, then you have this nice property that the control, this local control here, will converge to a unique equilibrium point exponentially fast. That's what it says. Okay, and what happened is that under this condition, this iteration is a contraction mapping, and therefore the conclusion follows. Okay, I think I am okay. I'm 2 minutes over, so let me just quickly stay without much detail. Is that what can we say about the equilibrium point Q star? Well, it turns out that suppose under conditions C1 and C2 hold, then the unique equilibrium point solves the following optimization problem, which is, suppose you want to minimize, let me write this down and just give a quick interpretation of what that okay, so this is sum of a j. Okay, so you solve this problem. What does this mean? So what I don't describe in detail is that this is a function. Let me just easier to write this. Cj Qj is Qj Uj minus, which is the inverse. Okay, so the point is, given a control function that you choose, right? So you can choose a control function to be something like this. So let me give you an example, which is a practical example. So this is the error Vi, and my control function Ui may look like the following, right? So it's strictly decreasing. So this doesn't satisfy C2 because there's a portion, there's a deadband, which is what people use in practice. Mathematically, it's not very convenient. So let's say if your Uj is something like this, right? Strictly decreasing, then there's a value Uj. Okay, so given a Uj that you choose, you can choose however you want to control. That's your Uj. There's a function that can be defined in terms of the control that you choose, right? Is the inverse of Uj. That's why we need the strict decreasing property of Uj. Then the inverse always exists. Otherwise, the same thing holds. It's just messier, right? So it's the inverse of your Uj, and then take the integrals and stuff. You can think of this as some measure of cost of the reactive power Qj. And that measure of cost, reactive power cost, depends on your control. So when you choose a control, you are sort of implicitly choosing a certain cost, imposing a certain cost on your reactive power. And this is the cost that you want to minimize when you converge to Q star. So that's what this term is. So your Q star will try to minimize this implicit cost implied by the control law that you choose. This is another control cost which depends on the X matrix that we saw earlier, right? Which is the which is a positive definite matrix, and this is quadratic form. So it is again because X is a positive definite matrix, and therefore this is a cos. And then the third one is a measure of the cos that depends on the deviation from the reference. Okay, so the deviation from the reference of this vector, this is a given quantity of this vector. So you look at this vector and look at the different deviation of this vector from the reference vref. That's this. Okay, and you multiply by the control Q, so inner product with the control Q. So this is somehow the implied cost of your control that you try to minimize when you converge. Okay, so that's the interpretation of the local control, and this local control, of course, is convenient because it's local, but it also has, but you can improve the properties, so it doesn't have some other properties and so on, and you can improve your control to have some other desirable properties, but at the expense of maybe some communication required between some nodes, right? So it's not entirely local, it could be distributed, so maybe you need only to communicate with your neighbors, for example, right? So that is the many things that you can design and prove using this linearized model. So this is just an illustration that the linearized disk flow model is really convenient. Okay, great. Sorry, we're running a little bit 7 minutes into the break. So we will take a break and be back at 11. Yes, so we'll be back at 11.